Once we understand momentum and how momentum is conserved in a collision, there are still a few more details about the different kinds of collisions that we need to understand. First, there are two kinds of collisions, elastic and inelastic. Elastic simply means that things bounce off each other. So, in an inelastic collision, two items collide and then they bounce off. So in my drawing here, the bottom is an example where they collide and bounce off. That's an elastic collision. An inelastic collision is where two objects collide and they stay stuck together, which means that the mass times the velocity of the two objects before the collision will simply be equal to the mass times the velocity of the objects after the collision. The difference is, in an inelastic collision, you actually combine the masses. So you could write the equation that the mass times the velocity of object 1 plus the mass times the object of velocity 2 is going to be equal to the new combined mass of the objects times the combined masses' new velocity. In an elastic collision, you simply write that the mass times the velocity of 1 plus the mass times the velocity of 2 before the collision is going to be equal to the mass times the velocity of 1 after plus the mass times the velocity of 2 after. Everything we've seen up till now is when two objects are hitting each other head-on. But what about when objects collide at an angle? Well, that's going to make things a little bit more complicated. In physics, when something is traveling at an angle, we generally break that down into its x and y components, which means we look at an angular velocity as two separate but combined velocities. In this case, we'd have a velocity going down and also a velocity going to the right. In angular collisions, the same rules of momentum still apply, which means that the mass times the velocity before the collision is going to be equal to the mass times the velocity after the collision. But because things are traveling at an angle, we actually look at it as two separate equations. We calculate the mass times the velocity for going up and down, and that momentum is going to be conserved. We also look at the mass times the velocity going left and right. And likewise, the left and right momentum is going to be conserved. Let's look at a sample problem. So we have ball A that's going to strike ball B at a 60-degree angle. Because ball A is traveling at an angle, our first step is to break its velocity down into its x and y components, meaning we look at ball A as traveling in two parts. Part 1 is to the right, part 2 is downward. When we break down the x and y velocities, we actually see that all the velocities combined form a right triangle, and they give us this angle of 60 degrees. So right away we should recognize that as our famous 30, 60, 90 triangle, which means we now know the ratio of the sides of the triangle. Remember, the short side opposite the 30, that's your shortest side. We'll call that x. The hypotenuse, or the slanted side, that's going to be twice as big as your short side. And the medium side, the side opposite the 60, is going to be the short side times the square root of 3. The problem tells us that ball A is moving downward and to the right at 12 meters per second. That's the slanted side, or the hypotenuse in our triangle. So we could write the equation that 2x is equal to 12, or x is equal to 6, which means we can fill in the rest of our triangle. So x is 6, and x root 3 is simply 6 root 3. Now we know all three velocities. We know the angular velocity, we also know the velocity going down, and we also know the velocity going to the right. Since we know the velocity of ball A in terms of going right and going down, we can also calculate the momentum that ball A has in terms of going right and in terms of going down. The equation for momentum is still the same, just mass times velocity. So in this case, the mass is 2, and the velocity to the right is 6 root 3. Or the total momentum to the right is 12 root 3. Likewise, we can calculate the downward momentum. Same equation, mass times velocity, or mass of 2 times the velocity of 6, or simply 12. Now, let's look at the momentum in ball B. Well, ball B isn't moving, so ball B's total momentum is simply 0. Let's look for a minute what happens after the collision. Initially, ball A is going down at an angle, so it has both a right and a downward movement. After the collision, ball A only has a downward velocity. Likewise, B only has a velocity going to the right. We know that ball A started with a downward velocity of 12 root 3. And because after the collision, ball B doesn't have any downward velocity, that means 100% of the downward velocity must have been retained in ball A. But ball A doesn't have any rightward velocity. It's not moving to the right at all. That means that A lost 100% of its horizontal momentum, and that momentum had to go somewhere. It had to go to B. So now we know that B has a horizontal velocity of 12, but a downward velocity of 0. Likewise, we know ball A has a vertical momentum of 12 root 3, but it also has a horizontal momentum of nothing, of 0. And then if we look at the initial and final momentums, you can see everything is conserved. We still have a total combined vertical momentum of 12 root 3 and a total combined horizontal momentum of 12, just like we had before the collision. If we want to go one step further and calculate the actual velocities of each ball, we simply use our momentum equation. In ball B, we know the mass times the velocity to the right is equal to 12. According to the question, ball B has a mass of 2, so his velocity must be 6. Ball A, same situation. Mass times velocity is equal to 12 root 3. Our mass of 1, so simply velocity is equal to 12 root 3 in the downward direction.